In this video, we will introduce the monad type class and we'll have a look at the functions that we'll need to implement in order to have a proper monad instance. But please keep in mind that we will have a more practical and probably more useful idea of what monads are capable of when we will play a bit with monad implementation in the next video. In this video, we are going only to introduce the function themselves, since of course, if we don't know what the functions are supposed to do, is very unlikely that we will be able to implement any monad instance. And as always, we'll ask to our friend GACI what is the definition of the monad type class. And alongside the definition, we already see that there are some known instances already implemented. Among those, we also see the maybe and the list, so we know that we will be able to try whatever function is defined for a monad, also with lists and maybes. And up here, we see the actual definition of the monad type class. And in the definition, we see that three functions are available for every monad, of which, well, one we already know, it only changed its name, but since, as we can also read here, each monad has to be an applicative too, well, this function, which is called return, is nothing much that what we call pure for applicative, and we see that there is actually no difference between this pure right here and this return right here, apart from this M, which in reality has to be also an applicative, which is what this F is meant to be in the pure of the applicative. So what is new in monads are these two functions, and actually here I lied. In fact, also this function is already defined for applicatives. We just didn't talk about the applicative version, but we see that this is the equivalent for this operator in monads. We see that also here the only thing that changes are the M with the Fs, but it's just the naming convention that changes. So the actual real superpower of a monad is this operator, which is also the minimal function we need to implement in order to have a monad. So we'll start right from here. And we see that this operator takes two arguments, one M of A, where M is the monad. So it takes a monad of anything, since we don't have any constraint on this A. And then a function that given an A returns a B, so another value of a type that may be the same of the input or also may not, so whatever type, wrapped once again in the same context, and then returns it. And from the moment that the returned value is also a valid input for the same operator, we can chain multiple calls of this operator, and this is actually what this operator is meant to do. And on top of chaining computation, since as we know, applicative represents computation in a given context, and that implies that also monads have to do something similar. But the real new feature of the monad is that when we chain two computations, we can get the value of the first one and we can use it in order to construct what will be the next computation in that context. And this is something that we weren't able to do with applicatives, well, at least not directly with the functions given, and for which the monad type class is used too. So without further explanation, let's see what this boy is capable of doing. And well, let's start by testing it using lists. As we know, the computation meant for list is to iter through the list. So the function expected as second argument will take as input one single element of the list per time. So I'll call the input list lm and then use this input into whatever expression substitute with this function. And remember that this function has to return a value in the same context we are working with. So it's expected to return a list in this case. And well, I will just return a list lm added with a 2, of course, wrapped into a list. And what we coded here is our famous add_choose function done in a monadic way. Well, actually, a proper monadic way will be to use the return keyword with the return element. And since the purpose of return is to lift a pure value into the context, this is the way you may want to use return. And well, now this function feels almost like we were in an imperative language and works just fine in Haskell. And not only works just fine, but as written here, this works for every monad, since we only use function defined into the monad type class. Therefore, it works also with maybes. And even if having a way to express computation in a syntax that feels almost like an imperative language is for sure a great feature, this is not the only reason for why monads are so important in Haskell. And in fact, the main reason is to have control on the control flow of a program. In fact, due to the lazy evaluation of Haskell, it is hard to predict when a computation will happen. So if we have side effects, it's hard to predict when those side effects will happen. But using this operator, now this computation depends on the result of the previous computation. Therefore, this operator alone is introducing some sort of control flow in Haskell, which is why side effects are handled in monad type class in the vast majority of the cases. And in order to have only the control flow feature without the need to depend from the previous computation result, we can use this operator, which is the bind without the equal. And well, from the type signature, we see that this operator too takes a value wrapped inside a monad, but as a second argument, it does not take a function that depends from the value of the previous computation. Rather, it takes just another computation using the monad and then returns it. And well, as written here, this type signature is not that useful, and we also saw that this operator has an equivalent into the applicative type class, but due to the type signature not being so explicit on why we would need this operator, this is the exact reason for which we are introducing this operator here. In fact, in the monad type class, you can think at the default implementation of this operator of being something like this, where the expression with which the bind operator, which does not really bind anything, is substituted with this expression, where we use the first monad we got with the bind operator, but the function that we should provide as a second argument to the bind operator totally ignores whatever was the result of the first monad and then just returns the second monad. And well, this function could also be written as const monad b. Recall that the const is a function that takes two arguments. If you don't know what this const is doing, there is a video exactly for this kind of utils. In any case, you can stick with this definition. And well, we said that the fact of relying on the previous computation result was the main reason for which we would use a monad. Why ever would we need such an operator? Well, we don't really need that, of course, since as we saw, there is already this operator, but the main use case of this operator is to only take advantage of the potential side effects that the monad A has to execute in order to unwrap this A to provide it here, and therefore is useful to introduce the control flow which is necessary in order to work properly with side effects. And of course, a similar operator was already present into the applicative since, well, as we saw, we don't rely on previous computation results, which is a feature that an applicative does not have to implement. So until now, we only saw how the function of a monad works, but we really did not even touch what monads are capable of. And in order to do that, I really think that the best way will be to have a more practical approach. And in order to achieve this result, in the very next video, we will implement a monad from scratch. So if you learned something from this video, you should consider to subscribe to the channel. If you really want to support the creation of this content, in the description below, you'll find a link that allows you to delegate your data to Harmonic pool and their interest on top of that. In any case, I want to thank you for your time. Remember to stay decentralized, and I will see you in the very next video. Bye bye.